Okay, so in the first assignment after the Thanksgiving Day, we're assigned to make a summary of all of those seven processes, and basically I would like to make a summary about their probability mass function and their expectation and their autocorrelation function. And all those seven processes are Poisson process, Poisson increments, Poisson impulse, semi-random telegraph, and random walk, and the last one is the Wiener process. Okay, I've written all those answers in the whiteboard, but there is also several things I'd like to say. As for Poisson process, for a given time, the Poisson process it's just a Poisson distribution, which we have already learned, or whose properties have been learned in probability course. So with this, so its mean value it's lambda multiplied by t and its autocorrelation function. We need to take a look at it's actually symmetric between it's symmetric about T1 and T2, so this actually holds. As for okay, the next one is Poisson increments. With this definition, it's actually a difference between two Poisson processes. We need to be careful that this is actually a discrete process in which this random variable xt could only get a number of discrete values. So we could write it in the form of that. This sounds like a Poisson distribution. Yeah, in fact it is. But if we're gonna take a but xt it's not a Poisson process. This is something we need to be careful about. But xt it's observes, if taken as a random variable alone, observes this Poisson distribution. So it also has this. So it has the mean value lambda and the autocorrelation function is here. As for Poisson impulse, which is a little bit tricky, we need to know that if the Poisson impulse from this origin is taking the derivative of the Poisson process. So in fact, it's just so what it can get with its values it can take, are just a summation of a number of impulses, but where those impulses but as for where those impulses are located and how many impulses are there, this is something that we should determine by a random process. So if those impulses if the number of impulses, which is n, already here, are given, and those the location of the impulses are given, that is ti, t1, t2, t3, blah blah blah, to tn are given. There is a probability, which I can deduce it from Poisson process, which means that those impulses must locate at exactly those places T1, which means there is only one count between T1 and T2. There's only one count between T2 and T3. Blah blah blah. So according to the Poisson distribution, this and also a property that then any non-overlapping intervals are independent. So the probability that such things happen equals to the multiplication of all those Poisson distribution, and the parameter are lambda multiplied by ti minus ti minus 1. So which means that between any two impulses there are no Poisson process, there are no counts. So well, as for this mean value, we could deduce it from this Poisson process, and we could just first do the expectation and then take the derivative. So we have lambda. The same goes to this autocorrelation function. We just do the derivative, take the derivative finally. Okay, as for this semi-random telegraph, are those semi-random telegraphs are those with this initial value 1 fixed, but it's a variant, but it resolves according to a random process. So we have anytime if it takes the value of 1, which means that there are there are even number of changes, which equal the probability of which equals that. It's a hyperbolic function, and we have the same for it takes the value of -1, which means that there are all number of changes, and the expectation value, we could just simply plug 1 multiplied by this and -1 multiplied by this, and we get this. As for its autocorrelation function, its expectation value of this in two different times can only take the two values too, which means 1 or -1. If it takes the value of 1, that means that the number of changes happen between these two timeline are even, and vice versa. So we could do this, and we get the final result. It's actually we take the absolute value. It contains the absolute value of this difference of these two times. As for the the next one, the random telegraph. The pure or fully random telegraph actually just add an extra random variable in this. We just add the initial condition. There's also a random variable. It has the half of the probability to take 1 and half to take the -1. So its expectation value is 0, and its autocorrelation function after some deduction. Well, get this. This is just some arithmetic calculations. There's nothing else to say. As for random walk, well, if we're talking about infinite times of coin tossing, this is a way more complicated issue. But the random walk has the property of it's a Markov process. So the values which the random variable at certain time could take, it's only dependent on its past, not on the future. So if we're going to take this binomial expression, just basically means that if we're going to take the value of r, which means we need to take a positive something and take negative something, so their difference is r. And take a look at this expression. If n plus r divided by 2, it's not an integer. This probability equals to 0, which means that is reasonable. So we could get that after some deduction. So obviously its expectation it's 0 because it's symmetric from up and down. And its autocorrelation function is the minimum of n and m multiplied by this step function, multiplied by s squared, whereas it's the length of steps that a particle make. The last one is the Wiener process. From its origin is the limit of this random walk. But we may as well take it as a process alone. It has the probability function of this normal distribution with this mean value 0 and its variance proportional to the parameter. It's alpha t. Alpha is a constant. So obviously its mean value is 0, and we're going to take its autocorrelation function. If we're going to take its autocorrelation function, we need to implement this limit process of random walk. After some assumptions, after some careful deductions, we could get this actually proportional to the autocorrelation function of random walk. That's alpha minimum of T1 and T2.